Hello, my dear doctor friends. I wholeheartedly welcome you for this CME on hypoglycemia. Needless to emphasize that hypoglycemia is the most important problem that we face when we treat patients of diabetes. In this CME, we are going to look at the pathogenesis, the counter-regulatory mechanisms of keeping the blood glucose in the very narrow range of 70 to 100 milligrams, and the diagnosis of hypoglycemia, the different types of hypoglycemia, and of course the treatment of hypoglycemia. As usual, this CME is also available on our website www.drsharma.in. In this website you can find several other CMEs of around 140 different CME topics of interest for free download. I request you to go to the website and take advantage of these different CME presentations. So let us now proceed to understand hypoglycemia. Before we go into hypoglycemia, we need to understand the glucose homeostasis. So the blood sugar or blood glucose is kept in a very narrow range of 70 milligrams to 110 milligrams in the fasting state, with a slight spike after the postprandial state up to 140-150 milligrams. How is this possible? This is because of two important hormones, the insulin and the glucagon. So let us start with a scenario where the patient's or person's blood sugar is on the lower side, less than 70. Immediately the alpha cells of the pancreas release glucagon. This glucagon stimulates glycogen breakdown and also the production of new glucose called neoglucogenesis or gluconeogenesis. With the breakdown of glycogen, new glucose is available into the system and new glucose is manufactured from the precursors by gluconeogenesis. Both these will increase the blood sugar. Of course, when the blood sugar is low, there will be also stimulation of the hunger, and we would take some food which contains the carbohydrate, which will be converted into glucose, so much so the blood sugar is brought to a higher level or normal level. Supposing, look at a scenario where the blood sugar is higher than normal, let's say 150, 200, like that. Immediately the beta cells of the pancreas, instead of the alpha cells there, now it is the beta cells of the pancreas that are stimulated, and they produce insulin, which in turn stimulates glucose uptake by the peripheral tissues, and also this movement of glucose, inward movement of peripheral tissues, reduces the blood sugar to normal levels. So in between meals, this is how the blood sugar is maintained at a lower stage of around 70 to 110 milliequivalents. So this is in nutshell the glucose homeostasis as we see here with the glucagon and the insulin. Whenever there is low blood glucose, glucagon comes into picture. Whenever there is higher blood glucose, insulin comes into picture. Glucagon produces input of more glucose into the system. Insulin removes the glucose from the system into the tissues. So this is glucose homeostasis. Whenever we have excess of glucose in the system, it will be stored as a fixed deposit in the liver, in the muscle, and to some extent in other tissues, adipose tissues, as glycogen. This process is called synthesis of glycogen or glycogen synthesis. Glycogen is the storage molecule or storage form of energy. Glucose is converted into a complex carbohydrate called glycogen and stored for needs. Whenever there is need, whenever the blood sugar falls, before we take some food to raise the blood glucose, this glycogen that we have stored in the liver or the muscle is broken down, and this will be able to keep up the blood sugar levels and keep us going until around 8 hours of time before we start eating further meal or snacks. So in general, up to 8 hours we will not have any problem as far as the maintenance of blood glucose is concerned. That is because of stored glycogen is converted into glucose by a process known as glycogenolysis. Of course, this 8 hours will be shortened whenever we exercise, whenever we are starving, whenever there is illness, and of course, most importantly, whenever the patient is an alcoholic. Because alcoholics, the glycogen storage in the liver is much lowered, and so much so, in these conditions like exercise, starvation, illness, and alcohol increase, alcohol intake, in all these conditions, the glycogenolysis is increased, so much so the ability to withstand fasting will be reduced from 8 hours to 4 hours or even less. What is gluconeogenesis? Gluconeogenesis is, neo means new, genesis is production. So, new production of glucose. That means glucose, even if you do not consume glucose, glucose can be synthesized from the precursors like the fatty acids, like the proteins, amino acids, protein breakdown products, amino acids. So, from the amino acids and from the fatty acids, glucose being synthesized is called gluconeogenesis. This occurs mainly in the liver and the kidney, and muscle and adipose tissue and kidney supply the fuels. The fuels are the fatty acids from the adipose tissue, and the muscle gives the protein, and the kidney also gives some of these precursors, and all these together are combined to form new glucose. Remember, brain can use only glucose and has got very little glycogen with it. So, it cannot withstand the hypoglycemia for a long time. It can sustain only a few minutes without glucose. Luckily, brain does not need insulin for the transport of glucose because in all other tissues, when the glucose has to enter the cell, we require a specific transporter called the glut, and these gluts are under the influence of insulin. But in the brain, the glut is there, but the type of the glut that is there in the brain does not require, a glucose transporter in the brain does not require insulin. That is the reason when we treat hypoglycemia, we don't require to give insulin. Otherwise, if brain were to need insulin, we would have treated every patient of hypoglycemia with glucose along with insulin. So, that is the situation as far as the homeostasis is concerned. Look at this diagram carefully. Arterial blood glucose, when there is a reduction in the arterial blood glucose or when there is an increase in the arterial blood glucose, the pancreas is informed and the brain is informed. Let us consider a scenario where the blood glucose is reduced. Immediately the pancreas knows that there is no blood glucose, so much so insulin is suppressed and glucagon is released. Insulin, when it is suppressed, it conserves the utilization of glucose and keeps the blood glucose up. When the glucagon is released, it acts on the liver and produces glucose from glycogenolysis, or the storage form of glucose is broken down and glucose production is increased and glucose availability is increased. Likewise, the low blood glucose is informed to the brain, and once the brain knows that the blood glucose is low, it releases several neuromediators, particularly sympathoadrenal outflow is increased, and sympathoadrenal outflow acts on the adrenal medulla to increase the epinephrine. It acts on the sympathetic postganglionic neurons, and the sympathetic postganglionic neurons produce norepinephrine and acetylcholine. So, these two neurotransmitters along with epinephrine, that is epinephrine, norepinephrine and acetylcholine, they produce the symptoms of hypoglycemia or the adrenergic and cholinergic symptoms of hypoglycemia. Immediately one will be urged to ingest carbohydrate or food, which again maintains the arterial glucose. Also, epinephrine acts on the kidneys, acts on the liver, and when these neurohormones are available in excess, they increase the gluconeogenic precursors like lactate, amino acids and glycerol, and these will be coming from the muscle and the fat, and of course the kidney, and all these precursors are pushed into the liver. Liver produces more glucose, so much so the glucose is maintained. So, the other accessory pathway for that is the brain, the pituitary is stimulated, pituitary produces growth hormone, excess of growth hormone conserves glucose again, or it releases ACTH. The ACTH is adrenocorticotrophic hormone, which acts on the adrenal cortex here. Here this is the sympathadrenal outflow through the adrenal medulla, and the ACTH through the adrenal cortex produces excess cortisol. So, growth hormone, excess cortisol will also contribute for maintaining the arterial glucose. So much so, whenever there is hypoglycemia, the things that come into play are, the first defense will be insulin, the second defense will be increase in the glucagon. First defense is reduction in the insulin, second defense is increase in the glucagon, the third defense is the sympathadrenal outflow, the accessory defense is through the growth hormone and the cortisol, and of course the symptoms are making us eat glucose from external source. These are the ways in which glucose is maintained in the body. So, let us say that we are in a fasting state. Fasting can be a short fast for around 4 hours, 5 hours, that is what we normally do between the meals. Overnight fast, prolonged fast. In the short fast, what happens is, body utilizes the free glucose that is available in the bloodstream to up to around 20%. The remaining 75% of the need is met by the breakdown of glycogen from the liver. Supposing we are on an overnight fast for doing some blood test or something, say night 8 o'clock to morning 8 o'clock, 12 hours, glycogen breakdown accounts for around 80% or 75% of the volume of the glucose maintenance in the blood, and 25% of it, of the glucose in the blood, comes from gluconeogenesis. So, in the short fast, it is the free glucose which is like the currency or cash in the hand, and glycogen, the bank withdrawal, and in the case of overnight fast, we have the bank withdrawal from glycogen, that is 75%, and then gluconeogenesis, that is from the fixed assets like the proteins and the fat are burnt down and then to produce glucose. Supposing one were on a prolonged fast, like a willful fast or fasting because of non-availability of food, only 10 grams or less of liver glycogen remains and all the glycogen is spent out. Gluconeogenesis becomes the only source of glucose at the time. There will be muscle wasting, there will be adipose tissue breakdown, and muscle protein is degraded for amino acids. Lipolysis generates ketones which act as an additional fuel. Ketones by themselves can yield energy other than glucose. That is how the body tries to maintain the glucose in spite of fasting. But sooner or later, these counter-regulatory mechanisms fail and one need to get the actual intake of food, and that is how one cannot survive fasting for a little longer than 3 or 4 days. That's most important for us to understand, that we require continuous supply of fuel, the carbohydrates or any food for that matter. So, to summarize, whenever there is high glucose, it is toxic to the cells. Advanced glycation products. These advanced glycation end products are very toxic to the cells, and the glucose transporter is informed about the high levels of blood glucose. Beta cells of the pancreas come into picture. The effector hormone is insulin, and this insulin increases the glucose uptake by the muscle and fat tissue and thus lowers the blood glucose and prevents the accumulation of AGP. This is what happens in diabetes. In diabetes, this effector hormone is not functioning properly, either it is deficient or it is not effective. That is insulin resistance, so much so glucose uptake is reduced and then blood glucose remains higher and AGP will produce the toxicity to the cells. But normally in a non-diabetic person, the insulin takes care of it and prevents the surges in the blood glucose. Whereas when the blood glucose is very low, energy needs are not met, immediately the body is informed, glucose transporters know that there is a little of glucose there, alpha cells of the pancreas are stimulated, glucagon, the counter-regulatory hormone to insulin, is the most important one released from the pancreas, and this stimulates the breakdown of glucose in the liver, glycogen in the liver to glucose, and raises the blood glucose. So these are the immediate defenses for high blood sugar and low blood sugar, which are like two sides of the same of a balance, and if this balance is critically maintained nicely with the input of insulin and glucagon being matched to the needs of the blood sugar, so much so the blood sugar is kept within a narrow range, as we have already seen.